So today we're going over direct versus inverse variation. Now, direct variation is what we're so far have been used to. It means as x increases, so does y, or in essence, they're increasing in the same direction and at the same proportion. The basic directly proportional relationship is y equals kx. So we have this generic formula, which we see right here, and you should recognize because this is the most fundamental equation of our line, our slope-intercept form. Instead of saying mx, we put k, k being the constant of variation. Now, an inverse variation means the opposite. As x increases, y decreases. In essence, they're going in opposite directions. What a lot of people get confused with is that inverse variation, they think, well, as x increases, y decreases, as in x is getting more positive, y is getting more negative. Almost, but not quite the same thing. X is getting bigger and y is getting smaller. That's what we mean by inverse variation. And again, it's at a constant rate. And we're going to use this formula right here. The idea being that if we have some constant form, so if we take both of those and we actually solve for k on both versions, what we'll have is we'll have this set of relationships. We have our y equals kx, which is our direct, and we have our inverse right here. Y equals k divided by x. If we solve for k on both of these, here I'd have to divide by x. So I have y divided by x is my constant of variation. Over here, I'd have to multiply both sides by x. So I'd have xy is equal to k. If k is to remain the same, let's say, for example, on this one, let's say k is equal to 5. So we have k is equal to 5. Well, if y is going to go up in value, x also has to increase in value. So if I give an equation, I say I want k to be equal to 5, and I have my y is equal to 5, well, my x would have to be equal to 1, because 5 divided by 1 would give me that 5. If I wanted y to, let's say, double to 10, x would also have to double to 2 in order to keep that ratio of 5. That's what we mean by direct relationship. As y increases, x increases at that same rate. Not the same is said about inverse. And actually, let's pick a smaller number. Let's pick something like, let's say k is equal to 1. No reason why k needs to be equal to 1 or 5. I'm just picking 1 because it's less math to do on the fly. So if k is equal to 1, let's say y is equal to 1. X would also have to be equal to 1 because 1 times 1 would give us the 1. If, for example, y doubled and switched to 2, well, x would have to be cut in half to 1/2 because half of 2 is 1. We see that as 1 is getting bigger, 1 is getting smaller. Likewise, we could have taken a different route, or let's say we make y smaller. So if we cut y in half to 1/2, well, then x would be forced to double. So we see the fact that they're moving in opposite directions. And that's really what's at the core of direct versus inverse. Are they moving at the same rate, or are they moving in opposite directions? So having said that, we have a couple different types of relationships we're going to talk about here. We have what we call, normally it would be called end behavior, but I have some inclusive behavior in here. With direct, we see that as x approaches infinity, so does y. And more than that, y also approaches infinity at the same proportion. As x approaches 0, so does y. They both approach at the same rate, the same proportion. And in fact, you've seen these types of graphs quite often. Like we said, this is the same thing as the formula for the equation of a line. You can see like this, let's call this f of x, or you might see one like this, g of x. In fact, no matter what's going on, they're either increasing or decreasing at the same rate. They're lines. Now, the same cannot be said about the inverse. Remember, as x approaches infinity, y has to be getting smaller, so y is going to be approaching 0. Likewise, the reverse is true. If x is approaching 0, y is approaching infinity. They're going in different directions, not positive and negative, but big versus small. And we're going to be going over this type of graph over the next several videos. And the idea is that as 1 is getting bigger, let's say as x, it'd be a good idea to label these things. So as x is getting bigger, y is getting smaller. So let's pick some arbitrary point. And as we go to the right, we know that as x gets bigger, y is getting smaller. The same can be said in reverse. As x is getting smaller, y is getting bigger. We see that it forms this type of curve. And the same is true on the other end of the spectrum as well. As x is approaching negative infinity, y is approaching 0 from the bottom. And as x is approaching 0 from the left, y is approaching negative infinity as well. So we're going to call this f of x. And we realize that this can be true in the same that we can have a positive, negative line. Well, this would be our positive line. It went from low to high. This would be our negative line, or our negative inverse relationship. And we'll call this g of x. Perfect. So we have two different types of shapes, both positive and negative, of two different types of relationships. So how do we tell if the graphs are either direct or inverse? Well, that goes down to what we discussed at the beginning of this, where we had our solutions for k. What we know is the fact that if it's a direct relationship, when we take our y and divide it by x, we get k, which is a constant of variation. So let's test out a few of these. Do this right here. So if I were to see if this was direct, I would know that y divided by x is going to give me my k. So I'm going to make a portion of my table, which is all my y divided by x. So I'm going to take 2 divided by 1, which is 2. 4 divided by 2, which is also 2. 6 divided by 3, and 8 divided by 4. What we notice right here is that I have a constant of variation. So I know that this is going to be a direct relationship, and my k is equal to 2. If I were to have tried to find the inverse, I would have to multiply the 2, and I'd make an xy table. I'd say, okay, x times y is going to give me a 2 here, an 8 here, an 18, and a 32. We notice that it's not the same number, so it's not, again, what we call a constant of variation. So I know it's going to be my y divided by x, or my direct relationship. And if I graphed it, I would see one of these shapes. Let's go ahead and graph it and see what shape it has. So if I graph 1, 2, 2, 4, 3, 6, and 4, 8, I notice the fact that yes, indeed, my graph is going to be a straight line. So I have a direct relationship. Now, for the next one, I'm going to do the same thing. I'm going to test to see, is it a direct or is it an inverse relationship? And the way that I find that out is by taking my y and dividing by x. So if I take y and divide it by x, 5 divided by 1 is going to give me a 5. If I take 5 halves and divide it by 2, let's come over here and let's do a quick piece of sketching. So if I take 5 halves and divide it by 2, I know that this is actually a 2 over 1. And when I divide fractions, that's really just saying 5 halves times 1 half, which is 5 fourths. So my next one is 5 fourths. And if I follow that same logic, that's 5 thirds divided by 3, or 5 thirds times 1 third, which is going to be 5 ninths. 5/4 divided by 4 is really saying 5/4 times 1/4, which is 5/16. Again, what we notice here is that we're not a constant of variation. There is a variation, but it's changing every piece along the table. But if I take my other type of relationship, my inverse type, and I plug this along and I multiply the two numbers, well, 1 times 5 is going to give me a 5. 5/2 times 2, well, the 2's are going to cancel out. We have a 5. 5/3 times 3, that makes the 3's cancel out. And 5/4 times 4, the 4's cancel out. What I have right here is I see that I have a constant of variation in the inverse direction. And furthermore, I notice that that constant of variation is going to be a 5. And so let's see what this graph would look like. Well, I'd graph 1, 1, 2, 3, 4, 5. I'd graph 2 and 5/2, which is 2.5. 3 and 5/3, which is about 1 2/3. And then 4 and 5/4, which is about 1 1/4. And what we notice that's going on here is we have this general shape. Now, beyond just the general shape, if we go back to our sketches that we did earlier, we notice that the graph seems to curve down and over, but it doesn't seem to go into the negative area. And now let's think about why that is. Well, as I keep increasing my x, my y has to keep getting smaller. Can we think of a number that we've increased x to that would cause my y to be 0? Because it looks like I'm having to take y and divide it by that number. So what number could I divide 5 by to get it to be equal to 0? We might think a few different things, but in the end, we're going to get to no matter how big of a number I take, if I try and say, okay, 5 divided by 1,000, well, that's a really small decimal. Let's say that's 0.123. Actually, 0.005. Ignore that. I would have 0.005. If I tried an even smaller number, let's say 5 divided by 100,000, I would just get 0.00005. And if I kept increasing the length of my denominator, I would just have, let's say, 5 divided by, let's call this 1.000. So there's an indeterminate amount of zeros. Well, I would get a number like 0 repeating 5 or 0.5. I would still have a number at the end. So no matter how big my number is, it doesn't actually ever reach 0. So it's going to curve down, but never touch. And we're going to talk about what that is here in one of the future videos. But let's go ahead and let's try the last one. Go ahead, pause the video, see if you can't figure out which type of variation this is, direct or inverse, and see what the constant of variation is. Unpause it when you're done and see how you did. Okay, so if I try the direct, I know I'm going to take y and divide it by x, which means that I'm going to have, in my first case, a 3. 3/2 divided by 2 is the same as saying multiplied by 1/2, so 3/4. Already we know it's not going to be direct. If I take 1 and divide it by 3, well, that is 1/3. If I take 3/4 divided by 4, that's the same as multiplying by 1/4, so 3/16. And what we notice, this is definitely not a constant. So our only hope is to give this a shot. I'm going to multiply the two numbers, which would be 3. Here the 2's are going to cancel out, so I'll have a 3. I'll have a 3. And the 4's will cancel out, so I'll have a 3. And what we've noticed is that, yes, in fact, I have an inverse constant of variation at 3. And if I were to attempt to graph it, I would see that that is going to be the case. Perfect. And there we go. Okay, so today we're going to be working with the reciprocal function, or another way that many people often name this function is we call it the rational function. Keyword being rational, because rational base word is ratio, we're creating a fraction. Reciprocal meaning the equation has been flipped, so again, we're creating a fraction. So no matter what you actually see the name of it is, we're talking about a function that has been flipped and in essence creating a fraction like we're going to see here. Now, a couple different things we want to cover first. The reciprocal function is an expansion of the inverse function where, albeit instead of viewing from the other variable's perspective, we're moving in opposite directions of scale. We talked a little bit about this in the prior video where as one is getting larger, one is getting smaller. And that's what we're talking about opposing directions of scale. The reciprocal function is also one of the core parent functions. This is a relationship shown in simplest terms of a single operation or procedure. Instead of going with the direct multiplication factor, we're dividing. So again, keep an eye on specifically our number 1, which is the parent function, just to see what it looks like, because all other versions of these graphs are going to be variations of this theme. This particular function has 2 asymptotes. We've seen with our exponential equations that we have a horizontal asymptote where a graph is going to curve down but never actually touch it. But this one actually has a second one, which is a vertical asymptote. And we'll see where that pops up here in just a moment. And we remember that these are lines that the graph will approach but never actually reach. If it touched it, it wouldn't be an asymptote. So let's go ahead and we're going to try and graph this thing. Now, before we've actually seen the shape of the graph, we're going to have to use what we call the brute force method. We're going to have to plug in a lot of points and kind of see what shape begins to emerge as we go. And being the parent function, typically we're going to want to pick a few variables right around the number 1. So let's go ahead and let's set up a table. So x comma y. Let's set up a few variables around the number 1. So let's say -3, -2, -1, 0, 1, 2, and 3. A nice variety of numbers all around the number 0. Let's see what they get us. So each one of these we're going to divide by that number. So 1 divided by that. So I'm going to divide this one by -3, -2, -1, 0, 1, 2, and 3. Let's take a look at where this leads us. So for the first one, 1 divided by -3 is just -1/3. That works well. Same with the next one. We'll get a -1/2. This one can fully reduce. We'll get a -1. And here's where we encounter our first problem. I cannot divide a number by 0. That makes the number too large. So what we have right here is I have something that doesn't exist, or what we like to call as undefined. And so we know the fact that if it's undefined at this point, we know that x cannot be this number, otherwise I would get an invalid result. So I know that x cannot be 0. And as we keep moving on, that reduces down to a +1, a +1/2, and a +1/3. Okay, let's go ahead and graph these points and see kind of what shape seems to be appearing. So I have a -3, -1/3, a -2, -1/2, -1, -1. I don't have any point right there. 1, 1, 2, 1/2, and 3, 1/3. Okay, so it looks like I've got a couple different options that are arising here. I don't know if this is going to be, looks like I have a curve right here and a curve right there. I don't know what is going on here in the middle. It could be, boop, it bounces. It could do a gradual curve. So I need to figure out some more points in between these. So I'm going to create a secondary table, x, y, with a few values between 0 and -1 and 0 and +1. So let's just go with some simple fractions. Let's say How about -1/2 and -1/4? So I'm getting 2 points in there. And then on the other side, I'm going to plug in 1/4 and 1/2. So the same 2 points, just on opposite sides of the 0. Okay? So as I plug them in, I know it's 1 divided by the number. Okay? And so our first notice is that when we're going ahead and we're plugging in fractions, we're going to keep change flip. So I'm going to keep the 1, change that to multiplication, and flip that to a 2/1 or just a regular old -2. I'm going to do the same all the way down. I'm going to flip them into a version where it's 4/1 or just a -4. This is going to be a 1 times a regular 4 and a 1 times a regular 2. So I get -2, -4, +4, and +2. So let's plug those on our graph and see where we're at. So if I'm -1/2, I'm at -2. Okay, that's not what I was expecting. I was expecting for it to come back up. And then if I'm at 1/4, I'm at -4. Okay, so it seems to be I'm moving away from this set of dots. So I wonder if it's going to curve up through here somehow. Let's take a peek. So at 1/4, I'm at, definitely not curving back up. It's up here. And then at 1/2, I'm at 2. So we see the graph appears to be moving in 2 completely separate directions, or what we like to call as divergent. And even when it approaches x, it seems to be approaching 2 different directions again. So if I were to connect these with a line, what we would see is we'd see a graph like this. Now sometimes if you plug it into your calculator, what you'll see is you'll see a graph that goes down and you'll see a vertical line and the graph coming up. Not necessarily the way the graph looks, that's just the way the calculator is trying to connect this point with this point, and it just connects it with a straight line. These actually, as we see, don't touch on this graph. So what's up with this x = 0 point? Well, that's actually one of our asymptotes. We know that if I draw a line right through x = 0, we notice it's right between where these 2 lines seem to bend towards, but not actually touch. So x = 0. So that's actually what we call our vertical asymptote. We notice we have, it looks like they're both approaching a horizontal value. It's never actually reaching 0 here, and it's never actually reaching 0 here. So let's go ahead and draw a quick horizontal line. And we know the fact that y cannot = 0 either. And so what we've seen is that we have inadvertently found our 2 asymptotes. We have a vertical asymptote where x can't = 0 because I can't divide by 0. And I have a horizontal asymptote where y can't = 0 because no matter how big of a number I throw in there, if I throw in a number like 100, I would have 1/100th. And I would be really close, but I would never actually make it to 0. So, boom, we have our first parent function. So let's move on to something a little different. This time, instead of graphing 1 divided by x, let's try 3 divided by x. And take a minute and see if you can't figure out what you think is going to change about the graph we see here when I increase the constant of variation, that number on top of the fraction. And as we work through here, see if your prediction works out. So again, we don't really know what's going on with this graph. We haven't seen too many of them just yet, so we're going to have to do what we call the brute force method again. And I'm going to plug in some values right around 0, just like what we did before. I'm going to plug in like a -3, -2, -1, 0, 1, 2, and 3. I know this time instead of saying 1 divided by, I'm saying 3 divided by. So I'm going to say 3 divided by negative 3, 2. Ooh, look, I'm dividing by 0 again, and just like before, we know what's going to happen at this point. We know right here in the middle, we know that x will not be able to equal 0 because I can't define at 0. So we're going to see that asymptote pop up right here in the middle again. So before we even graph the thing, we know the fact that it hasn't moved to the left or to the right because we know that x cannot equal 0 right here. So however the graph is shaped, I know there's going to be a left and a right side roughly right there. But we don't know whether the graph is flipped, if it's stretched, if it's how it's going to be moving. So let's go ahead and simplify a few of these and see if we can't graph a few of these points. 3 divided by negative 3 is negative 1. That's a negative 3 halves, negative 3, positive 3, positive 3 halves, and positive 1. Well, if I compare to my parent function, what I've noticed is that each value seems to have increased by 3, both on the negative side and on the positive side, which means that we must have taken our graph and stretched it by a factor of 3. So let's take a quick peek and see if that is true. So negative 3, negative 1, negative 2, negative 3 halves, negative 1, negative 3. Yep, that looks just like this, except for everything's moved a little farther away from the axis. In fact, if I move 1, 3, 2, 3 halves, and 3, 1, yep, looks like we're doing the same thing. And we don't actually need to create our secondary table right here because we know how the behavior works as it approaches this line. We know that the graph is approaching this but never actually reaching it. The only thing we might want to be sure of is it going to approach anything other than that 0? But we notice on each side it's equally distant away from this. This is 1 above, and at the same distance to the left, it's 1 below. So we can safely assume that, again, it will not actually approach, or I mean, it will approach, but it won't actually touch this line right here. So y still will not be able to equal 0, and we can continue our graph out in this direction and in this direction. And boom, we figured it out just with a few points. So same thing, but we know that that 3, so the 3 stretched the graph. Vertically. It's been moved just like that. Awesome. So let's do a few more. Let's see what would happen if I took this and said, hey, how about I take a 2 up there, which we know what that's going to do. I know I'm going to stretch the graph by a factor of 2, but let's put a negative out front. What would that look like? Well, let's give it a shot. We're going to create an XY table. We're going to plug in our handy-dandy values. Negative 3, 2, 0, 1, 2, and 3. In this case, I'm taking a negative 2 divided by. And what I'm going to assume is I'm going to put the negative in the top, so I'm going to treat that as a negative 2 divided by this number. Divided by negative 3, divided by negative 2, divided by negative 1. Ooh, I have that 0 again. And so again, we notice that so the top number changing and the negative sign doesn't seem to have affected this part of the graph. It looks like that vertical asymptote of x not being able to equal 0 has remained unchanged with either of those changes that we've put forth. I know that I'm going to put my label up here because there's more room. So x can't equal 0 right here because, again, I can't take a number and divide it by 0, even if that number is negative. Let's simplify a few of these and see what we get. It's going to be a positive 2/3, positive 1, positive 2. Again, we notice when I divide a negative by a negative, I'm getting my positive sides. Let's see, a negative 2, negative 1, and a negative 2/3. Okay, so from what we saw previously, if we compare that to, let's say, our parent function, I noticed that what was negative over here is now positive, and what was positive is now negative. So it does look like the graph has flipped. Let's go ahead and let's graph a few of these and see if it doesn't prove that point right there. So negative 3 and 2/3. Negative 2 and 1. Negative 1 and 2. 1 and negative 2. 2 and negative 1. 3 and negative 2/3. Yep. So we see as we're approaching this vertical line right here, it does look like our graph is increasing over here. And as we're approaching it from the right, it looks like our graph is decreasing. And again, if we look at the same distance away from our asymptote on both sides, they're both at a negative 2/3 and a positive 2/3. So it's safe to assume that we've discovered our horizontal asymptote still has not moved. We know that y still cannot equal 0, which would mean that this is going to curve out to the left and this is going to curve out to the right. And if we compare that to our prior parent function, we see not only has the graph been stretched a little bit, but also what was on the top flipped down to the bottom, and what was on the bottom flipped up to the top. So the graph literally changed orientation, which we talked about. Even though the graph isn't connected, this is a positive fraction, and we see the graph is in the positive quadrants, or it's going in a line even if the line isn't direct. This being a negative fraction, we notice that if I were to connect these points in a general trajectory, I'd be going from the upper left to the bottom right, which would be a downward or negative slope of sorts. Perfect. And so for the last one, I'm not increasing the top. It looks like I'm increasing the bottom. So I want you to pause the video, give this one a shot, unpause it when you're done, and see how you do. But before you do, see if you can't predict what's going to happen when I not increase the top, but increase the bottom. Okay, so let's give this a shot. I'm gonna make a table of values with my x, y. I'm gonna plug in my handy dandy values. Just like that. And now I'm gonna take 1 and divide it by 2 times that number. Pardon my small writing. Having to squeeze in a lot here. So if I take 1 and divide it by twice that number, 2 times negative 3, 2 times negative 2, 2 times negative 1, 2 times 0, we know what's going to go on right there. And as we work our way down, well, we see the fact that this one right here is going to be 1 divided by 0, which is, again, undefined. So we know for the 4th time, x cannot be 0. We have that vertical asymptote has still remained unchanged. It's a pretty tough little asymptote right there. We tried changing the top, we tried changing the bottom, we tried making it negative, and it's just not going anywhere. Let's work out a few of the others. So this is 1 divided by negative 6, or negative 1/6. 1 divided by negative 4, or negative 1/4. 1 divided by negative 2, or negative 1/2. This is 1/2, 1/4, and 1/6. So if we graph these, let's see, negative 3, negative 1/6. We're really small. -2, -1/4. -1 is at -1/2. Half, 4th, 6th. So what we see going on here is it seems to be we notice that as it's approaching the line, it is getting bigger, but it's doing so at a much slower rate. So the graph must be curving like that. Albeit I might have touched physically here. I know the graph is not actually going to touch that purple line right there. And that one's curving down, even if it's doing so at a much slower rate. And then we notice if I move equal distance on each side, I'm at +1/6 and -1/6. So it's safe to say that that horizontal asymptote also has not changed. So y still cannot equal 0. Perfect. So if we compare that to our parent function, what we notice is it seems to be that there was a little bit more space vertically in between the points. This was squished. So when I'm taking a number like 1 divided by x and I put a number larger on the bottom, what I know is that's taking the graph and it's squishing it. Where what we had done earlier was we were stretching it. Here, we're squishing it. So top means stretch, bottom means compress. Actually, let's go ahead and write that real quick. So negative will flip or reflect the graph. And then a increase of the denominator coefficient compresses the graph. Perfect. And there we go. So today what we're going to be working on is finding asymptotes. In a prior video, what we looked at was when we graphed the rational function, we ended up finding these vertical and horizontal lines where the graph kept approaching but never actually touching. So we're going to ask ourselves, is there a way to find them just by looking at the equation? And the answer is yes. We talked about there are two different types. There are vertical asymptotes and horizontal asymptotes. Now with vertical asymptotes, they're found in the denominator. If we remember, those were when we tried to divide by something that ended up making the denominator 0. So with rational functions or with reciprocal functions, what we'll notice is the fact that when we start getting quadratics, we can factor these into multiple factors, which means there can be multiple vertical asymptotes. We're basically going to set each one of those equal to 0, because if any part of the denominator is 0, the whole thing is 0. So we know there can be multiple vertical asymptotes. Now, the horizontal asymptote, this is found with the leading terms and their coefficients. We're going to see how that works. And especially horizontal asymptotes might not exist when it looks like it might be a rational function. It might simply be a type of polynomial or linear function or some variation thereof hidden in disguise as an unsimplified fraction. So again, horizontal asymptotes might not exist, but the vertical asymptotes, if we ever have something like that, they'll pop up. So let's go ahead and let's try and start finding some of these. So let's pick, how about blue? We're going to find our vertical asymptotes in blue. We know these are found in the denominator. There can be more of them, but we're going to set each factor equal to 0. Well, if I look at the bottom of my fraction, I see an x plus 1. So I'm going to set each one of those equal to 0. So x plus 1. Not really sure what I did there. I think that's an equal sign and a 0. Started to be with a slash through it, and we just curved it. So we're going to go with it. X plus 1 equals 0. To solve for that, what we'll do is we will subtract a 1 on each side, which cancels that out, and we'll have an x equals -1. So let's try and plug in the -1. Well, 2 times -1 is -2, divided by Well, negative 1 plus 1 is 0. So I know the fact that it's not x equals 1. I know that x cannot equal 1. There's my vertical asymptote. I'm going to have a vertical line through the negative 1 on that graph. Let's pick a different color for the horizontal. For the horizontal asymptotes, what we're going to try and find is the leading terms and their coefficient. So the way we do that is we pick the highest power of x. Here I notice that it's just going to be x to the first. I'm going to pick the ratio, which is where we get the term rational expression, of their coefficients. Here my coefficient is a 2, and on the bottom my coefficient is a 1. So I know that y cannot equal 2. So boom, we have our vertical and our horizontal lines of where the graph is going to bend, and we can graph points around those. So let's try another one. Let's see. For our vertical asymptote, we know we're going to set the bottom, x plus 6, equal to 0, and we're going to solve, which means that quite simply we're going to subtract 6, which is going to cancel it out, and x equals negative 6. I know if I try and plug that in, I'll be at the top will be a positive 24. On the bottom, a negative 6 plus 6 will be a 0. I can't put 24 into 0, so x cannot equal negative 6. There's a vertical line on the graph at negative 6 that the graph is going to try and approach but can't actually get to. For the horizontal asymptote, we're going to take the highest power of x. Again, it's going to be x to the first, or just that single x. And I'm going to take the ratio of the coefficients. So a negative 4 over a positive 1, or y cannot equal negative 4. And what we'll see is the fact that no matter what we try and plug in, we're not going to be able to get a negative 4 out of that graph. Awesome. So what happens if they both have coefficients in their denominator or on the leading term? Not too much different happens. We have vertical asymptote where that 3x minus 1. In this case, I'm going to have to add 1, so 3x equals 1, and then divide by 3. So x equals 1/3. I know if I try and plug that in, the top will be 4/3. The bottom, 1/3 of 3 is 1. 1 minus 1 is 0. We know that that cannot happen. So I have a vertical line at x equals 1/3. For the horizontal asymptote, I'm still looking at the first power of x, which on the top is going to be a 4, and on the bottom is going to be a 3. So I know that y will try and approach 4/3, but it'll never actually make it there. Perfect. So now that we've kind of gotten the gist of it, take a gander and see if you can't figure out what we might be doing here when I have these x squareds. What that's going to do to my vertical asymptote, what is that going to do to my horizontal asymptote? See if you can't come up with an explanation on your own. Well, if we take this, I know that my vertical asymptotes require that I take the denominator and set each factor equal to 0, according to our rule right here. Set each factor equal to 0. But I have a quadratic. Well, that just means that we're going to have to factor this. So the top, I'm just going to leave it as is, x squared, and I'm going to try and factor this quadratic. Now, I could use the quadratic formula, but I noticed that these are two perfect squares with a different sign between them. So this is just a difference of squares, which means that's going to be x plus 2, x minus 2. We know because if we FOIL that out, I'm going to get an x squared. The plus 2x minus 2x are going to cancel out, minus 4. So boom, I have that. So I'm going to set each one of these equal to 0. X plus 2 and x minus 2. I'm going to subtract the 2 here. And I'm going to add the 2 here. Perfect. And so let's see if I can't plug these in. If I plug in a negative 2, well, that would be 4 up top. And then negative 2 squared is 4 minus... Can't plug in that one. That doesn't work. If I try and plug in a 2, that's a 4 up top. 2 squared is 4, minus 4 is 0. Well, can't plug in that one. So I have not 1, but 2 vertical asymptotes right here because I have a quadratic in the denominator. For my horizontal asymptote, I see the highest power that I have is an x squared. So I'm going to find the ratio of their coefficients, which is just going to be a 1 over 1. So y cannot equal 1. Awesome. So why don't you give this one a shot real quick and see if you can't predict what the two horizontal and vertical asymptotes are going to be. Okay. So if you've given it a shot, we know the vertical asymptotes mean I need the factors of the bottom set equal to 0, which means I'm going to have to factor this. So I'm going to leave the top. In the bottom, I notice that again, I have perfect squares on both sides with a different sign. So I'm going to take the square root plus the square root and the square root minus the square root. And some of you might say, well, hey, you can factor out a 4 out of that, but that's okay. It's not actually going to affect the asymptotes themselves. So with this, I'm going to take a 2x plus 8 and set it equal to 0, and a 2x minus 8 and set it equal to 0. Here I'm going to add or subtract the 8, so 2x is negative 8, and then divide by 2, which is negative 8 divided by 2 is negative 4. Over here, I'm going to add the 8 and then divide by 2, so positive 4. And if I try and plug either one of those in, let's see, negative 4 squared is 16. 16 times 4 is 64, so 64 minus 64. I can't do that. That's an asymptote. If I plug in a positive 4, well, it's the same thing. So 4 squared is 16 times 4 is 64. Minus 64 is 0. That's also an asymptote. Can't do that. The horizontal asymptote, I'm looking at the squared powers, which gives me a negative 9 over a 4. I know that it'll approach but never actually reach that number. Awesome. So again, give it a shot on number 11. Pause the video, see if you can't figure out what's going on. Okay, so assuming you've paused the video, you'll notice that again, for our vertical asymptote, we have a difference of squares, which means I'm going to need to take this and say square root plus square root minus square root. And that way I can factor that and set each of these equal to 0. So I'm going to have an x plus 11 and an x minus 11. X equals negative 11 and x equals positive 11. If I try and plug either one of these and square it and take away 121, well, can't divide by 0, can't divide by 0. So I have my two vertical asymptotes. Now, the new thing is what's going on right here. For my horizontal asymptote, I always take the biggest power of x, which is an x squared. And some lessons, the way they teach this is that when I have a larger power on bottom, there's an automatic 0 asymptote. Now I think automatic kind of takes away the joy from what we just did here. If I don't see an x squared on top, I know there is one, but it's been zeroed out. So there must be the equivalent of, let's do this in, let's say green, so that way it steers clear. I know that there is an x squared, but the only reason I don't see it is it must have been multiplied times 0, because then I wouldn't actually need to write that. So I know the x squared term up top has a 0 coefficient. On bottom it has a 1. 0 divided by 1 means that y is going to approach but not actually touch 0. So we see it's not necessarily an automatic asymptote. We're still doing the same process of what we've been doing, but it always ends up with 0 when the larger power is in the bottom, because that means there is a 0 in the top. And so that kind of answers our next question is, does the leading coefficient of the numerator matter when the denominator has a higher power? And this leads us to say no. The asymptote ends up tending towards 0. So we know the asymptote really just kind of automatically heads towards that 0 feature. But now that we've seen how we figure out where the asymptotes are, let's go ahead and see if we can't use that to graph a few functions. Because what we've done previously is we've done the brute force method where we just plug in value after value and see kind of what we get. So let's see if we can't use that to our advantage. Well, we're going to take this and make a vertical asymptote and take that x minus 3, set that equal to 0, which means that x cannot equal a positive 3. So what we're going to do over here is I'm going to say, okay, 1, 2, 3, and take a value right there. And for the horizontal asymptote, we're going to plug in y. Let's see, that's going to be the first power of x, which means that's a 4 over a 1, or y cannot equal 4. So I know is 1, 2, 3, 4. Okay. Probably should have scaled my graph a little differently because that's going to be way up there. And then let's plug in a few points. Now, realistically, I know how the graph is going to behave on either one of these points. It's going to either approach, it's going to be either above or below, and it's going to approach this either from the bottom or from the top, and it's going to approach this either from the bottom or from the top. So I only really need to plug in 2 points, one on the left and one on the right. And it doesn't matter which point I plug in. I can plug in a point right next to the line or farther away. So I'm going to plug in a point right here. Let's just say at 1, 2. So for my x, y, I'm going to plug in the value of 2. That's on my left side. On the right side, 3, 4, I'm going to try and plug in the value of 4. So I'm going to say 4 times that number divided by that number minus 3. Or 4 times that number divided by that number minus 3. This number being 2, this number being 4. Let's see, so that's going to give me an 8 over negative 1, or negative 8. This is going to give me a 16 over 1, or positive 16. Okay, well, I know I don't have 16 on my graph, and by my scale, I don't have negative 8 on my graph either. So really should have drawn this a little farther to scale, but what we're going to end up doing, if we really want to, let's plug in another point to the left. Let's plug in a 0, just so we have something to put on this thing. So if I plug in a 0, that would be 0 over negative 3, or 0. Perfect. So let's do the graph in green. So at 0, 0, I know the fact that this negative 8 was also in this quadrant of the graph. So I'm going to curve down towards that negative 8, even though it doesn't actually show up on my graph. And I'm going to curve this up towards that asymptote, because I know regardless which points I pick, it's going to slowly approach that. And then this over here, again, should have picked a different scale, but this is in pen, so it's a little too late. It's going to be just like that. And we have our graph. Lo and behold, we didn't need to graph nearly as many points, even though this was a much more complicated reciprocal function than what we've been doing. We find the 2 asymptotes, we graph a point on the left and the right to double check to see which side it's going to be on. Do one more. We're going to take this one. Actually, it's a good point. Go ahead, pause the video, see if you can't use the asymptotes to graph the function using a minimal amount of points. Okay, so assuming you've taken a go at this, we're going to take our vertical asymptote and set each factor in the denominator equal to 0. But I have this negative sign right here. So I'm going to have to do one of two things. I'm going to have to assign that negative either to the top or to the bottom, because I can't just have a negative sign sitting out there when I'm trying to find these asymptotes. So I'm going to put it in the top, which would make that a negative x minus 2. It'd be a 2x minus 4. Awesome. So now where we got that negative x minus 2 is I distributed that negative to both of the top versions. So that'd be like multiplying the x times the negative 1 and the 2 times the negative 1. So we get that. We could have put it in the bottom, and it wouldn't have actually changed the vertical asymptote. Here, if I took the 2x minus 4, let's say I put it in the bottom, and I had a negative 2x plus 4, we'll see that both of these end up being the same thing. This is a 2x equals 4. This is a negative 2x equals negative 4. When I divide by 2, x is 2. When I divide by negative 2, a negative and negative cancel out. So we see the fact that no matter which version I pick, if I put the negative in the top or the bottom, I'm going to have the same vertical asymptote. For the horizontal asymptote, I know I'm looking at x to the first, which in this case is going to be a negative 1 over 2. And that's it. That's all she wrote. Now, kind of learning from our mistake on the first one, even though this is a 2 and a 1/2, we're going to go ahead and we're going to make these scales by 2s. Just so that if worse comes to worse, we need more room, we have it. So I'm going to draw a vertical asymptote at positive 2, which is going to be right here. So I know that x can't equal 2. And I'm going to draw a horizontal asymptote at y can't equal negative 1/2. Awesome. Okay. So really all we need to do is we need to test a point on the left and on the right to double check to see, is it going to be going through these two or through those two quadrants. You might have been intuitive and noticed that negative sign means that it's going to be a downward curve. But just on the off chance, let's plug in a number that's to the left, which in this case, I'm going to plug in a 0. A number to the right, I'm going to plug in a 4 and see what happens. So in this case, I'm actually going to revert back to our original function right here, which is a negative plus 2 over plus 4. I'll plug in a 0 and a 4. This is going to be a negative. Let's see, it's 2 up top. That's 0 plus 4 is 4, or a negative 1/2. Okay, so I kind of picked and chose there. That's actually a 2. It's going to be a minus 4 in both of these, which is going to make that a negative. So negative over negative is going to make that a positive 1/2. Kind of scared me for a second because I was like, hey, hold on. We can't equal the negative 1/2. But just a typo. Didn't copy it down right. And so for this one right here, this is going to be a negative. Let's see, 4 plus 2 is 6. 2 times 4 is 8. Minus 4 is 4. This is going to be a negative 3/2. So let's see where this will be. So at 0, we are at positive 1/2. And at 4, we are at negative 3/2. So we're right there. And so again, we notice that the trends are a downward curve right there. I know that it's going to be in this quadrant, whoop, and in this quadrant. Whoop, whoop. Perfect. Let's actually thicken that up so we can see it a little better. And again, you could have picked any values on the left and on the right because you know the general shape of this graph. You could have picked a value like 6, 8, or 10. You could have picked a value like maybe not 2, maybe 3, and you would have gotten a value somewhere right in there. And the points aren't necessarily important as long as you're picking on the left and the right to see which quadrant it's going to be in. So now that you've seen that, you'll notice one of the things that's happening is when we go to simplify our vertical asymptotes, we create a fraction that can be reduced. And you might ask yourself, like, okay, can I make my life a little easier? Can I go ahead and factor out one of those values, and would that make any sort of a difference? Well, your answer would be yes, you can actually factor it out. If you run into a question like this, what you could do is in the top, you notice the fact that both of these look like they've been multiplied by 10. So if you factor out a 10, both of these look like they've been multiplied by 20. That would be an x minus 3. You can actually factor out those numbers and then reduce the fraction. So this would be a 1/2 x plus 4, x minus 3. Again, that would be an x plus 4 or a 2x minus 6. So we can either treat this is actually a really good way to figure out almost immediately our horizontal asymptote. Because if I know x is to the first power, boom, I have my coefficients right there. I know that y cannot equal 1/2. Now, this is a factor, so I could either set this or this as my vertical asymptote as the factor of my denominator equal to 0. I could either say x minus 3, or I could say 2x minus 6. Regardless, I'm going to get an x equals 3 that I cannot plug in, or 2x equals 6, which means x, again, cannot equal 3. We notice that it is a redundant value. So when we go ahead and plug in our value of 3, and again, we're not going to make the same mistake as earlier. I'm going to do everything by 2's, which means I have a vertical asymptote at 3. I have a horizontal asymptote at 1/2. Perfect. So I really only need to plug a value in on each side. So I'm going to plug in 4 and 2. So 2 being my left value and 4 being my right value. So if I plug in the value of 2, I'm going to use my reduce fraction right here. I'm going to say that's going to be something plus 4 over 2 times something minus 6. Let's not make the same mistake we did earlier. 2 times that something minus 6. Okay, so this is going to give me a 6. 4 minus 6 is -2. That's a -3. This is 8. 2 times 4 is 8. Minus 6 is 2, which is a positive 4. So we notice is that 1/2 is positive. And if we graph this, see at 2 we're at -3. We notice that that positive coefficient out here is going to mean a positive slope. So again, we're expecting something in this quadrant. Boom, right there. And then when I hit 4, we're at 4. We got something in this quadrant. So we know the shape of this graph is similar to our parent function, albeit it was shifted. There we go. Okay, so today we're going to be finding asymptotes, and this is the second part of what we've done prior. Today we're going to be graphing functions that have not just one, but more than one vertical asymptote. And now the shape of these points between these is going to be comparable to our quadratic for the most part. However, there is an exception to the rule with these asymptotes, and that's when we have a 0 or zeros, misspelled there, but oh well, that exists somewhere that an asymptote does not. So let's see what this means here in a minute, because typically speaking, when I see a function with this is what we're going to call, let's see, what color do we want to put this in? We're going to say that this is one vertical asymptote because we have one factor in the denominator. Here, where I have two factors in the denominator, that means I'm going to have two vertical asymptotes. Here, when I have three, I'm going to have three vertical asymptotes. So if I have one vertical asymptote, I'm not actually going to sketch this function. I'm going to sketch a function that just has one vertical asymptote. So we're going to draw one line like this. Again, this is not this because that would mean that x plus 1 equals 0. That would be x equals 1. My asymptote would be over here. This is just a general sketch of a function with a vertical asymptote. So I'm going to draw the same one on both sides. And we know that each function with a vertical asymptote is also going to have a horizontal asymptote. So we know that, let's do this in the color blue, so that way we don't get confused between the one or the two vertical asymptotes. So if I draw my vertical or my horizontal asymptote in the same spot on both graphs, we know the shape of a generally positive function means that it's going to be an upward trajectory, which means it's going to be in this quadrant or in this quadrant. Oop. Okay. And if it's negative, remember we're going to have a downward line. So it's going to be somewhere in this lower quadrant when it goes off to the right. And vice versa, it's going to be in the upper quadrant off to the left. And there's a couple things we're going to take note of here as we move forward with a few of these things. We notice that the shape is generally positive, which means they're in diagonals. Here it's generally negative, but again, they're in diagonals to each other. The second thing is we're going to notice is that I have one point on my graph where I'm crossing the 0. So I'm going to put just a point right here because we're going to get back to that here in just a moment. And we notice that if it wasn't in the positive version of the graph, it might be a flip version where it's the negative, or the asymptote might be a little higher. But that 0 is perfectly fine. When I have two vertical asymptotes, let's go ahead and let's draw two of them. And why not? Let's draw them same on both sides. So this must be like a difference of squares on the bottom because the asymptote is equidistant from the y-axis. I'm going to draw our same general horizontal asymptote. Okay. So we know the fact that with a generally positive graph, the graph, no matter what it's doing, is going from the bottom to the top. Maybe doing other things, but it's going to end up in the positive direction. So the final result is going to be over here in this quadrant. Even though it's no longer a quad for quadrants because there's 6 of them, I don't think hexant sounds quite the same. So I know it's going to end up right here. And from the prior experience, what we saw is it's going to move at a diagonal. My next one's going to be down here. But if I pick any random point, let's say this point, I know it can't touch this axis. So if I try to curve up towards this, I'm going to have to curve away from it at some point. I might be able to curve a little later, but at some point I'm going to have to curve down. So I know that the graph is going to have a generalized downward trajectory. It's going to have a curve going down. And if I follow that same path going up, now it may do like a little loop-de-loop and pull, but it can't hit that corner. So it's not going to continue to curve up towards there. At some point, it's going to have to come back down, and it can't curve up. So again, it's just going to mirror itself going down, trying to stay away from those two asymptotes. Can't actually approach this one. It can, but it'll have to bend back. And so that's why we say it resembles a quadratic, because it looks something similar to the way quadratics look. Now it might be more square or lopsided, but the general idea is that there's a U-bend in there. And it's also diagonal. And that means that on the flip side, over here, we have that. And what we notice is the fact that with these graphs, I have multiple opportunities for the zero, but unlike with this one, if it's not going to be in the left, or if it's not going to be in the right, it'll be in the left, or if it's not going to be in the top, it'll be on the bottom. This one, let's say my zero was somewhere in the middle. Well, it would have to be in this graph. It would not be able to be in these two. And we're going to come back to that here in just a moment. So think about how the zeros are going to affect the graph. If I have more than one zero, like let's say here, here, and a third one, what would that mean? Okay. Same thing with the generally negative. We know the final result is going to be over here. We know the diagonal would mean that the graph is going to have this weird boxy U shape up here because we move through the diagonal. And then if I move through the diagonal again, I notice it's going to be just like that. And if we revert back to and remember kind of how the shapes of our polynomials look, I know with the polynomial with the quadratic, when that quadratic was on top, it went in a U shape. And kind of what we're seeing is we're seeing a generalized U shape even though it's in three distinct pieces. It went from up to down to up. If I had a negative quadratic, it would go from down to up to down, and we see the graph doing that general shape as well. Even though it's doing some weird wonky bendy things, it's the general overall shape. Here with our three vertical asymptotes, so let's draw our same two. But I'm going to draw a third one right here. Boom. Well, following the same course of logic, and we need our horizontal asymptotes as well. Getting ahead of ourselves. Okay. We know with our generally positive, it's going to end up over here, which means the diagonal, I'd have my U shape right here. And diagonal, I would now have a secondary U shape over here. So I have more than one quadratic-esque shape. Perfect. And so what we see similar to if that was a cubic, I know the cubic is going to curve up, down, and then end up going up, and we see that graph doing the same thing even if it's through these weird shapes. Likewise, a generally negative, it's going to have that same shape, but each one of these is going to be flipped. Go through the diagonal. And go through the diagonal. Awesome. So the main point that we want to take away here is that the rational functions always move at a diagonal to each other. It goes down, up, it goes up, down, up, it goes down, up, down. They always move at diagonals. So we mentioned earlier what happens when we start breaking those rules with zeros. So we haven't gotten to the point where we've graphed these yet, but we want to take a look at what happens if I have a zero in the median part of one of these quadratic-esque curves. What does that do to the graph? So you can't really see the horizontal asymptote on this because it goes directly through the axis. But let's say there's a zero on the left third. Looks like I have two vertical asymptotes. Well, what we know is that, let's assume positive. We really could do this in both ways, but we're going to assume a positive curve here. What we know is that the graph is going to end up in this direction. which means that here in the middle, it's going to have this weird downward curve. Because again, it moves at a diagonal. Here, it's going to have a diagonal curving up. But wait, hold on. If it has a 0 right here, the graph is going to hit 0, but I didn't think I was allowed to hit the asymptote. The answer is you're generally not, but if there's a 0, a weird thing happens. Your graph is going to curve almost through your asymptote, or if you want to look at it from a complex version, it's going to curve behind your asymptote and curve up from the bottom. So it's going to pass it, and it's going to cause this nice little arc, but then it's going to curve up and approach your asymptote from the other end. So if we extend this graph out a little further, what we see is the graph is still attempting to approach that asymptote, but it kind of missed it, and then it's coming back, almost like a planet that got looped around a large object, albeit it's never going to hit that object because it's in almost like a circle. In this case, it's just going to curve and slowly come back towards there. So likewise, if I had a 0 on the right, what I know is that my graph is going to be in the positive direction at the very, very end. Unfortunately, that means that my positive direction, in this case, if I have a 0 right here, it's not going to be curving up because it has to approach that asymptote. That must mean that I'm on the tail end of one of these guys, where I'm curving and I'm going off towards the asymptote in this general direction. Let's extend that a little bit further, which would mean that my graph actually curves through the asymptote, or if you want to look at it complexly, behind it, where it curves up, goes a little bit over, and then bends and starts coming back down from the positive side, because we're assuming this is a positive graph. But unlike prior, when I'm going down right here, I have to move at a diagonal through my two intersection points, which would mean that my quadratic curve, or quadratic-esque curve, it's not actually quadratic, is curving up. And then again, a diagonal. This last piece would be curving down. So what we notice is, albeit we were expecting something as a generally positive to be up, down, or up, down, up, here we got down, up, down, and up. And it does this weird little twist thing. Likewise, if I have a 0 in the middle, let's stick one smack dab in the middle. We know the graph ends up in the positive direction, so the farthest right point is going to be a positive, which means that this point right here must be approaching from the negative side. And as it approaches this, we know that the only way it can hit that is if it curves through. So some of you might say, well, why can't it actually hit it and curve down? Well, remember with the quadratic, if it touches the x-axis once and only once, that means there's actually two zeros there. They're just so close together they actually touch. So we know it can't actually hit and curve down, because that would mean there'd be multiple zeros in the middle. Okay. And as we move forward, we know that now that we're up, we have to assume the graph is in the downward quadrant on this section. Perfect. Because again, we see the distortions of the graph. If we went even further and we said we had two zeros on the left, let's give it boop, boop. We're assuming positive, so I know that it's positive over here, which means that it's curved right here. Which means as I hit, this must be the upward curve, which means right there it's curving through that. Let's make those zeros a little bigger. And then it's curving above that, so that it can approach the axis or the asymptote from above, if we extend that a little further. Just like that. it does this weird little, and it really does appear to be revolving around that point. So if I had multiple zeros, that would just mean it's orbiting the axis, or orbiting the asymptote. If I had 2 zeros on the right, it's doing the same thing, just in the other direction. I know that my rightest point must be that point where it's curving up and over, because my last point has to be assumed to be positive. That means it must have curved below, which means that this is curving up. And if I move at my diagonals, awesome, so we have that. So again, we're starting to approach this thing where it seems to be orbiting a two-dimensional shape, which implies some other type of motion. We'll get to those in later sections. But the zeros in the middle, we talked about it has one of two possible choices. If we're assuming generally positive, I know that I'm going to end up over here. And as I approach my graph right here, I could either assume those 2 points are at the same, or I could assume those 2 points are at 2 separate points. So I have option 1, which says those 2 points are at the exact same point on the asymptote, where it kind of goes up and kisses the asymptote, where it touches it for a single moment in time, and then bends back down. Because we know with a quadratic that touches, that's actually 2. Or a second option is I could draw something like this, where it curves up and goes through like that. So either way, starting down, it briefly dives into the other hextant and then comes back down. And because it's in the downward direction as we move off, again, we're back in the upward. Perfect. So finding those zeros is going to be an important point for what we're about to do. So now that we've covered that and we've kind of seen how the general shapes are going to be, let's practice on a few of these guys. So for our first one, we have a reciprocal function with 2 factors in the bottom, which means real quick we can find our vertical asymptotes by setting x plus 1 and x minus 1 equal to 0, which means I have an asymptote at -1 and at +1. We further know that our horizontal asymptote, well, those aren't quite finished, so I'm going to have to go ahead and FOIL this. X plus 4. Let's see, x times x is x squared. X times -1 is -x. Positive x, -1. I can combine these two terms right there, which means x plus 4 over x squared minus 1. Okay. So now my horizontal asymptote is going to be off the x squared values, or 0 over 1, or just y cannot equal 0. The last thing that we want to find, because this graph does have multiple vertical asymptotes, is we want to be able to find where those zeros, where those warps in the general shape exist, which means I'm going to need to find where the graph is equal to 0 using the top. So it's just going to be 1, x plus 4 is equal to 0, which means when the graph hits -4, I'm going to have a warp where it actually hits our asymptote. If our asymptote is on the x-axis, that is. Let's go ahead and let's put our vertical asymptotes. And from our prior video, we did a scale of 2. With this one, it doesn't look like we're going to need to do that. Or if we do, we're just going to go ahead and kind of wing it. So we're going to do the scale by 1s. So I have an asymptote at -1. And +1. Perfect. I have a horizontal asymptote at 0. So again, those warps are really only when our horizontal asymptote is at this point, We've talked if that asymptote is above or below that point, and the zeros aren't really a big deal. But, okay. So knowing that we have this weird thing that happens at -1, 2, 3, 4 right here, we're going to need to plug in one from each section. So when we build our XY table, we're going to double check that by plugging in an area over here. Let's say right is going to be, let's plug in a value of 2. I want to plug in something in the middle. Let's plug in a 0. And I want to plug in the left, but I want to plug in 2 values, one to the right of the 0 and one to the left of the 0. So I'm going to plug in, let's say, -1, 2, 3, and -5. I'm going to plug in on each side of that 0. And just to show that we're plugging in on the sides of the 0, right there, and there's an asymptote that separates and an asymptote that separates. Let's go ahead and try this out. I'm going to plug it into our final version because it's a little more condensed. Plus 4 over squared minus 1, plus 4 over squared minus 1, plus 4 over squared minus 1, plus 4 over squared minus 1. We're plugging in a 2, a 0, a -3, and a -5. Okay. So 2 plus 4 up top is going to give us a 6. 2 squared is 4, minus 1 is 3. It's going to reduce down to 2. 0 plus 4 is 4. 0 squared is 0. Minus 1 is -1. That's going to be a -4. 3 plus 4 is 1. -3 squared is 9. Minus 1 is 8. That's 1/8. Right here, -5 plus 4 is -1. -5 squared is 25. Minus 1 is 24, which is already reduced. So let's see how this looks. I know that my coefficients out here is generally positive, so I was expecting something up over here. My right value of 2 gave me a number that is, in fact, up in this quadrant. So awesome. So we know that our first shape is exactly what we'd expect. It's a positive value. My next shape, I know that I should have a negative value because if I move through diagonal, I should get down here. And when I plugged in the 0, indeed, I got a -4. Boop, boop. Perfect. If I move through, I know I'm expecting something above, and I'm going to expect a curve below so that I can curve back up. So we're going to see if it's a positive right here, and after the 0, it should be a negative. So yes, in fact, I do have a positive of 1/8. It's a very small positive, but it is, in fact, curving up, so we keep that diagonal rule true. And then, yes, in fact, I get a -1/24. Again, it's not a huge negative, but what we'll see is the fact that the graph is going to curve down and then curve back up and slowly approach this line right there. Perfect. There we go. So having seen that, what I want you to try is I want you to try number 3. Give it a shot, see if you can't graph it, and see if you can't use those zeros in the distortions in the graph to predict what the graph is going to look like at all the extremes. Okay, so let's take a peek. So this one, I know this is going to be easy for my horizontal asymptote, but it isn't factored for my vertical. So I'm going to have to say, okay, because my A term is 1, I'm going to say what factors of 12 make a difference of 1? Well, let's see, that could be 1 and 12, 2 and 6, 3 and 4 make a difference of 1. So I'm going to split it into a 3 and a 4. So x and 3, x and 4 to get a positive 1. It's going to be plus 4 minus 3. There we go. So for our vertical asymptote, I'm going to say x minus 3 and x plus 4. Which means x can't be 3, and x can't be negative 4. So far, so good. For my horizontal asymptote, I'm looking for a squared power, which is going to be 0 over 1, or y cannot equal 0. And then for my last important point, I know there's going to be some sort of weird warp at x minus 2, which means that at x equals a positive 2, there's going to be a weird little warp going on here. Okay. Because my asymptotes are going to be a little more towards the extreme of my graph, I'm going to go ahead and let's do this scale by 2's. Give us a little more room. So I have a vertical asymptote at x equals 3. And x equals negative 4. And I have a horizontal asymptote at y can't equal 0. Perfect. And I have this weird important point at x equals positive 2. Right there. Oh, it's really close to my, my line right there. Okay, so we're going to test a point. Test a couple points here, actually. I'm going to test a point on the right. So say 2. Let's try a point at the right at 4. I need 2 points in the middle. One on the right side of my point, so I'm going to test the point, let's see, somewhere between 2 and 3. How about 2.5? And somewhere to the left, let's say 0. So I've got that right there. And then I need a number on the left. So negative 2, negative 4. How about negative 6? And we know there's asymptotes between these two. And I know the only reason I picked 2 in the middle is because there's a 0 between them. So let's see what they end up being. Now our expectation is, because my horizontal asymptote looks like it's a positive, it's a generally positive graph, I'm expecting a positive number, expecting the diagonal to be negative here and positive right here. And if I follow the diagonal, I should get a negative. So positive, negative, positive, negative. I should alternate as I go. But let's try it out. And we're going to try the factored form this time, simply because that looks easier to write. So blank minus 2 over blank minus 3, blank minus 4. Blank minus 2 over blank minus 3, and blank minus 4. Not blank minus 4, blank plus 4. Ooh. That would have screwed us up. Awesome. Let's plug our values in. So we're plugging in a 4, a 2.5, a 0, and a negative 6. Okay. So our predictions are, as we go down the table, we're expecting something. Where do we want to put these? So our predictions are going to be positive, negative, positive, negative. Let's see if those are true. So we have a 4 minus 2, which is 2. 4 minus 3 is 1. 4 plus 4 is 8. So that's 2 over 8 or 1 over 4. Positive. So far, so good. 2.5 minus 2 is 0.5. 2.5 minus 3 is negative 0.5. 2.5 plus 4 is 6.5. These are the same thing, so they cancel out. So that's a negative 1 over 6.5. I know we have a decimal and a fraction. Ran out of room, so we're not actually going to reduce that. But so far, we have a positive and a negative. We're on track here. 2, negative 3 times positive 4. That's a negative 2 over negative 12, which is a negative 1 over negative 6. So it's a positive 1, 6. Awesome. So positive, negative, positive. So far, so good. It's going to be a negative 8. Negative 6 minus 3 is negative 9 times negative 2. Let's see, that's 3 negatives, so my answer is going to be a negative something. 8 over 18, which is 4 over 9. Awesome. So now these are a bunch of really small fractions, especially for a scale of 2, but I think we get the idea of what the shape is going to be. We know that when we plugged in the value of 4, we had an answer of 1/4. So albeit it was pretty dang close, we're in the correct portion of the graph. We're in this upper portion because we have a generally positive graph. Followed by the 2.5, which was a negative, albeit I'm not even going to attempt to draw a negative 1 divided by 6.5. It's going to curve down, because it goes from 0 to negative as it moves closer. And as we move on the other side, we're at 1/6. So again, it's not moving up very fast, but we see the fact that the graph is curving through, which makes sense because there's 1, 0. It's not going to touch it and go back down. It's going to touch it and go through because there's our 1, 0. And then albeit we were expecting a negative, we got one. Negative 6, we were at negative 4/9. So we're almost at a half. So again, these are rather tightly bound, but our shapes and our predictions hold true. There we go.